Okay, good morning. We have discussed some of the numerical problems related to air conditioning in the previous class. Today we will try to see one very special case where we have to little bit deviate from the actual process of the air conditioning system in order to design the system. Okay, that special situation occurs if we have very high latent cooling load. Is this point clear? What are the situations where high latent cooling load can actually occur? For example, if you are sitting inside the auditorium, okay, or any such gathering, any such building where actually huge population or people are actually crowdedly placed inside the room. So, what will happen inside that space? Inside that space, you will be finding that our body will be actually releasing significant amount of latent heat. Okay, and ultimately that amount of latent heat has to be removed in order to reach the comfortable conditions. Okay, so it means that when and second situation could be if outside is extremely humid, then what will happen? We typically have some infiltration. For example, if you go to places like Bombay, Goa, which are close to the sea, okay, so there what happens typically, the air contains significant amount of moisture. So if you have to maintain inside the comfortable conditions, whatever the small amount of infiltration is taking place, and even for the purpose of ventilation, you are actually allowing some amount of ambient air to come inside. That ambient air will be leading to significant amount of moisture addition into the room. Okay, so ultimately that will also be having significantly amount of latent heat load, latent cooling load. And third scenario can be process requirement. Okay, so you are doing certain process which involves high amount of humidity. Okay, and that process condition if you have to maintain, then also we will be having actually high humid cooling load requirements. Okay, so what are the challenge with the high latent cooling load requirements? The challenge is RSHF line under these scenarios becomes very steep. Okay, so if RSHF line becomes steep, what happens? This is my I, this is some point 1. So under these scenarios, 2-3 issues can happen. One issue could be that RSHF line will become so steep that it will not be, because what we have more amount of latent heat. So latent heat will be represented by a vertical portion. Okay, so if I have increase in the vertical portion, it means it signifies that I have more amount of latent. Is this one clear? So one thing could be that RSHF line will become so steep that it will not get opportunity to cross the GSHF line and even the saturated curve. Okay, so if RSHF line is becoming so steep that it is neither crossing the GSHF line nor it is crossing the saturated curve, in this scenario you will be finding that you will not be able to precisely determine the what supply state of the air, because supply state is something which is combination of the combined common solution of GSHF line and the RSHF line. The second scenario could occur that whatever your GSHF line is there, because ultimately that load will also be reflected on the cooling coil. So your GSF line can also have two possibilities. One possibility is that GSHF line is also not meeting the saturated curve. Okay, GSHF line at all is not able to meet the saturated curve. Or other possibility could be that GSHF line is meeting the saturated curve, but it is meeting saturated curve at extremely low TADP. So TADP is extremely low. What it means? It means that in this scenario, you have to maintain very low apparatus dew point temperature. So if you have to maintain very low apparatus dew point temperature, it means whatever the refrigeration unit which is maintaining the cooling coil temperature, its evaporator temperature will be very low and it will be operating from very low temperature to high temperature, it means pressure ratio across the compressor will be very large. In that case, the refrigeration system which we are using, that will become inefficient. Because typically we are talking about the summer air conditioning. So in summer, my surrounding temperature will be close to 45 degrees Celsius, where I need to maintain the condenser above than 45 degrees, say 50 to 60 degrees Celsius. And if my evaporator coil temperature becomes extremely low, say 2 degree or 3 degrees Celsius, then the COP of the refrigeration system will be extremely low. Is this one here? So these systems, if we have to handle, then there are three possibilities. What are the solutions? So there are three solutions. First solution is the same thing, that we should maintain low ADP. We can maintain very low ADP. Second solution is we will be choosing high ADP, and then in order to achieve the room RSHF condition, we will be doing reheating. Okay, reheating. What is reheating? I'll explain to you. Okay, so it means that first you are cooling and then again you are heating actually, and then you are supplying the air to the room. So this is called as reheating process. And third thing, you can use phase and bypass dampers. What is the meaning of phase and bypass dampers? In this process, what we do typically, whatever the recirculated air is coming from the room, significant amount of recirculated air is just bypassed without passing it over the cooling coil. Okay, and we allow only small fraction of air to pass over the cooling coil. So when we will be allowing very small fraction of air to pass over the cooling coil, then ultimately automatically the ADP will go down. Okay, so it will help us in maintaining the low ADP. At the same point of time, bypass factor of the air will also become extremely low. So if you have very low ADP and low bypass factor, then whatever the amount of air you are passing, that will almost try to reach that low ADP condition. Okay, so in this scenario, almost its entire moisture will be actually removed, the air which is passed over the cooling coil. Then this air, which typically has very less moisture, it will be adiabatically mixed with the air, recirculated air, which is bypassed without allowing it to flow over the cooling coil. Okay, and that will give you the supply state. Is this point clear? So this is just a mechanical arrangement to handle the things. Now what I will do, because the first and third scenario, the problem solving technique will be similar to the previous one, only difference will be coming in the value of the temperature and the way we are handling actually the flow rate of the air. Is this point clear? So let's talk about now the second type of situation where I have mentioned that reheating also can be employed for this purpose. So typically what is done in case of reheating, let me first quickly draw the psychometric diagram, and after this psychometric diagram, what I will do, I will try to explain this in detail with the help of an example problem. Okay, this is O2I. So if let me consider this is RSHF and this is ESHF. What is ESHF? Effective room sensible heat factor line. Okay, and say it is meeting saturated curve at very low temperature. Now if this ESHF is extremely low, in that case my COP will be low, so I need to look for the alternative options. So what I will do, I will try to use some modified ESHF line. So this line I call as nothing but my modified ESHF line. Okay, and then 0 and I will be mixing together to form state 1, and from state 1 I will be having actually GSHF line. Now GSHF and RSHF will meet at point 2. If I extend O and 2, then it will meet modified ESHF line at point 2 dash, which typically we call the actual supply state. Okay, and this is my this state over here will be 3, and process 2 to 3 will be my reheating process. I will again explain this entire thing with the help of one example. Okay, you have to understand one very important point over here, that when I drawn the room sensible heat factor line, room sensible heat factor line is not that steep. Why? Because it is corresponding to the conditions which are coming from the wall, but ESHF is becoming steep. Why ESHF is becoming steep? Because ESHF contains the bypass factor times, what it contains? Bypass factor times outside air sensible heat and outside air latent heat. So here we are trying to deal with the scenario where outside ambient air humidity condition is extremely large. So ultimately that is causing the significant amount of latent heat load, and it is only modifying or making this line steeper. Is this point clear? Point is clear or not? Okay. So maybe I'll try to explain this with the help of example, that will be more clear to you. So let's talk about numerical problem. How many problems we discussed? I think this is problem number 5. Okay, so let me read the question. The outdoor dry bulb and wet bulb temperature are 40 degrees Celsius and 28 degrees Celsius respectively. What is given? DBT, dry bulb temperature for outdoor condition, is 40 degrees Celsius, and WBT for outdoor condition is 28 degree Celsius. The indoor design condition in a laboratory are 25.5. So it means T indoor is 25.5 degrees Celsius and RHI is 50%. Relative humidity is 50%. Okay. The RSH and RLH are 70 and 40 kilowatt respectively. Is this point clear? There are 200 persons in the laboratory. How many people? 200, and the ventilation requirement is 0.56 cmm per person. Per person, how much cmm is needed? 0.56. What it means? It means that QV naught is nothing but equal to 200 into 0.56, which comes out to be, tell me the value, 112 cmm. We need to find TS, WS and QS. So what we need to calculate in the question is supply air state, that is volumetric flow rate, temperature as well as the humidity. Is this point clear? How to proceed? First tell me what will be humidity, Wi. What will be Wi? What will be W naught? Please tell me the values. Wi and W naught. What are the values for Wi and W naught? Check from psychometric chart.
0.0099 25 के लिए था वो
How much? 0.00
0.0
0.01023.
हाँ 25 है
And what about the other condition, outside condition? Now you have two things, DVT and WBT. WBT and DVT you have to locate intersection point. Please tell me. What is the value? Is it in the range? How much? Quickly tell me. Zero point zero two. Yes, 0.0191103. Correct. Okay. Let's see. We have calculated WI, W naught. Now next step is, can I calculate OASH? Outside air sensible heat. How much it will be? 0.0204 QV naught into T naught minus Ti. How much it is? OALH 50 times QV naught, W naught minus Wi. Tell me the values. Tell me values. Do it fast. 33.12 kilowatt. Second one. Okay, what is RSHF? What is RSHF? Very simple. 0.636. Let us also take one more data. It is given in the question that bypass factor is 0.05. Okay. So X is given in the question. Please note down this point. Bypass factor is also given in the question. It is 0.05. Okay. Anyone is having any doubt up to this point? If you know this bypass factor, can you go with the ERSH? What will be ERSH? 70 plus X times OASH. How much it is? X, I have already told you, 0.05 given in the question. ERLH 40 plus X into OALH, how much it is? 42.48. What will be ERSHF? Effective room sensible heat factor. Zero point 0.6278. Let's draw this effective room sensible heat factor on the psychometric chart. What I will be getting? Draw this on psychometric chart. This is my ERSHF. I have drawn it on psychometric chart. Whenever I am drawing it on psychometric chart, what is the value of ADP I am getting? Please tell me. What is the value of ADP I am getting? You have to calculate and tell me. Three point 3.8 degree Celsius. Okay, so ADP will be 3.8 degree Celsius.
चार्ट में पॉइंट्स कैसे निकलेंगे? पॉइंट्स के बाद
Divide linearly on the x-axis. Okay, 3.8 degree Celsius. Now, what is there? Two important points we need to note down. First important point is what bypass factor I have taken at present. 0.05, which is extremely difficult to achieve. In rare circumstance only you will be able to achieve this bypass factor if you are taking extremely low flow rate. Okay. Another point to note down is with this bypass factor you are getting very low ADP of 3.8 degrees Celsius. If you slightly increase the bypass factor to a value of say 0.1 or 0.2, you will be finding that further the ERSHF line will become more steeper and it will not at all cross the saturation. Is this point clear? So these are some of the practical constraints, and other than that, even if with an ADP of 3.8 degrees Celsius you operate the cooling coil, then the COP of the refrigeration system will be extremely low. Is this point clear? All are clear up with this point or not? Now this is the situation of a extremely high, latent load requirement. Okay, is this point clear? So in this scenario, what we need to do? What we need to do in this scenario? Please tell me. As I told you previously that we need to assume some higher value of ADP. So let me consider that my higher value of ADP is 11 degrees Celsius. to maintain what issues? Practical constraints. Is this point clear? If question comes, it will be given to you what value you need to assign. All are clear with this point? So I have assumed to maintain the practical constraints which just now I explained to you, I assumed the value of 11 degrees Celsius. Now, can I calculate corresponding to this value WADP? How? At 11 degrees Celsius, I will go to saturated state and I will note down the value of corresponding humidity ratio. So that will be my WADP. How much it is? 0.008197. Correct? Okay. Now, if you know this, can you calculate modified ESHF slope? Can you calculate or not? Please tell me. Can you calculate? Modified, because actual ESHF you have calculated. But if I have to calculate modified ESHF slope, then modified ESHF slope will be nothing but 1 divided by 1 plus how much? 0.2451 into delta W by delta T. From here, can you calculate the slope? So if you calculate the slope from here, it comes out to be, it means, sorry. Yeah, how we will be calculating the slope? This is my point I. This is my point I. And what is my new value of ADP? This is T dash ADP. So if I join the line between T dash ADP and I, what I will be getting? Modified ESHF. Modified effective room sensible heat factor. Is this point clear? And its value comes out to be, if you can calculate, you can easily calculate now. You have drawn the line delta W by delta T. Okay. So its value comes out to be 0.74396. What is the value? 0.74396. Clear? Now, this modified value is something which I have arbitrarily set. Okay, because I assumed the value 11. I have not calculated it based on the actual ratio of effective sensible heat and actual ratio of effective latent heat. Is this point clear or not? So what I have to do now, in effective room sensible heat, if I add some quantity which I am calling as Q reheat, and similarly in the effective room total heat, I add this quantity Q reheat, such that this reheat value is to be selected in such a way so that it satisfies this equation. Okay. So what was ERSHF? 71.66 and ETH was 71.66 plus 42.48 plus, in all the cases I have this Q reheat. From this equation, can I calculate Q reheat? This will be giving me that Q reheat is nothing but equal to 51.787 kilowatt. Remember this point very, very carefully. How this point will be now helping us to solve the problem. Now, what is my actual, on this modified line, what is actual sensible load? Actual sensible load is, what was ERSH plus Q reheat? That is the actual sensible load on this line. It must be equal to 0.0 204 into what? QVS, supply state volume, into Ti minus TADP. If I assume that, basically it will be equal to Ti minus Ts. Okay, let me assume my supply air state is this. This is my supply air state S. Then if this is S, then this will be X, this will be 1 minus X. So if I have to calculate the value of Ts with reference to Ti, it will be coming Ti minus TdP into 1 minus X. Is this one clear or not? Because
modified ESHF means 0.2 नहीं आएगा, 245
sorry, 0.25
बन जाएगा, 245 होगा.
245 comes when you have to, yes, that is correct, 245 will come. But how it will come? Because you are assuming that what are the conversion units on x axis and y axis. Okay. How this comes? What will be the slope? kg water divided by degree Celsius. Okay. So if 1 unit of this is equal to 10 mm and 1 unit of this is equal to 100 mm, sorry, 100 mm, then what you will be getting? You will be getting some multiplication factor. So when that multiplication factor comes over here, then your value comes as 245. Okay. If you don't account for that conversion factor in terms of length scale here, then in the delta W by delta T you have to multiply that number. Is this point clear or not? This is just a geometric parameter. For example, 1 degree Celsius in one graph can be written equal to 1000 mm. Same 1 degree Celsius on one graph can be written equal to 10 mm. Point is clear or not? Then if you calculate the slope just on that graph and you don't take care of what scale you are using, then that value will be corresponding to that particular scale. So what you have to do, you have to make first this value independent of the scale. So when you make independent of the scale, you have to note down when you are observing delta W by delta T, what is the value of scale on that plot. Please practice this. This is a geometric parameter. It will not take much time. That's why I am not explaining this in detail. Okay. It's a simple geometric thing. You can try by your own. But you see over here, what typically is effective room sensible heat. Effective room sensible heat is nothing but 0.024 into QVS into Ti minus Ts. All of you agree to this point? Now same thing can be written as 0.0204 QVS and Ti minus TADP into 1 minus X. If you write it in terms of bypass factor. I have explained you on the graph. This is X, this is 1 minus X. Now you can do it. You can do it easily. So from here, how much is QS? .285 cmm, and if this is this, then QVR will be QS minus QV naught, and it is 327.285 mm. Okay, if I have to calculate state 1, which is obtained from mixing of QV naught and QVR, then state 1 will be what? QVR into Ti plus QV naught into T naught equal to QS into T1. From here T1 will be 29.197 degrees Celsius. If I have to calculate T2, then T2 will be simply equal to T ADP plus okay. So you need to assume this state is 2, this is S, and if this is state 1, then this is 2, this is 2 dash, and state S is somewhere over here, and 2 to S is something your reheating process. Two to S is your reheating process. Okay, all are clear with this point? So it means first you are cooling air extremely low, and then you are allowing this to heat so that it can reach the supply state in such a way it can meet RSH and RLH conditions. Is this point clear? Now can you calculate T3? RSH will be nothing but equal to, what will be RSH? 0.0204 QVS into Ti minus Ts, and that will be equal to 70 kilowatt. From here if you calculate, your Ts will be becoming 17.69 degrees Celsius. What it means? It simply means that this I must write T2, sorry, here I have done mistake. This simply means that my air after the cooling coil is coming at temperature of 11.91 degrees Celsius, but whenever I am sending it to the room, it is sent at temperature of 17.69 degrees Celsius. So it means after the cooling coil I have to use a heating coil as well. Is this point clear? So you have to understand this question very well, because the major idea is this type of situation is when we are designing the air conditioning system for scenarios where latent cooling load on the room is extremely large. Okay, so then this type of special arrangement has to be considered. It means where you are designing the system for high humid conditions, like for Bombay, Goa, if you have to design air conditioning system, then in your cooling system there has to be one heating coil as well. Okay, what should be the load on the heating coil, what should be the load on the cooling coil, you should be able to understand from this example, and accordingly you can replicate for the given conditions. Is this point clear? Okay, we will stop now.